Okay, thank you, Chairman. Thanks, everyone, for being here. I recognize that this is the last session of the conference, so we'll try to get through this as fast as possible and with as little pain as possible. So as you said, my name is Chris Regular. I'm a Master of Applied Science candidate at Ryerson University in Toronto, Canada. And today we're going to talk to you about a study we did in collaboration with York University on using data analytics and machine learning to enhance BIM-enabled facilities management. So we'll quickly go over, or not quickly, but we'll go over the study that we did at Ryerson. We'll go over our results, and then we'll go over some of the future work we're going to do, which was sparked by this study, and then after which we'll open the floor for some questions. So the idea behind this research is very simple, and all it is that facilities management produces a tremendous amount of data. And that data is produced through maintenance records, maintenance requests, previous equipment failures, etc. And that data can become extremely onerous on the facilities management team because it's a lot of information to deal with, but also that information can be leveraged to support facilities management and ideally support root cause analysis. So currently at Ryerson, we're working on using data analytics and BIM to enhance facilities management. And in this study, we did that through two tasks, essentially. We did automatic classification of work order requests through machine learning, as well as spatial visualization of the requests through BIM integration. And we currently just finished creating a recommender system of follow-up questions to provide additional information to the facilities management team. And as I said before, the goal of this is to support root cause analysis and identify maintenance trends and clusters in such a way where we can find a single problem that's contributing to several other issues. Okay, so currently users at Ryerson submit work orders through three platforms, either through email, telephone call, or an online form. And depending on their background, the level of detail within these descriptions is highly variable, which we'll talk about in just a bit. But the idea I want to get at here is that when they're submitting the work order, they're submitting a description of the work order, and they're not describing exactly what the work order is about. So it's up to facilities management to determine exactly what type of problem it is, whether it's HVAC, plumbing, electrical, etc. So the current workflow consists of a facilities management staff member analyzing the work order submitted through any of these three platforms, and then determining what sort of problem that is. And as I said before, because there's so many work orders coming in, this is creating a bottleneck in the system where facilities management isn't able to keep up. So what we're suggesting is that a computer program evaluate these work orders in order to not only define the type of problem that's occurring, but also to link it to the BIM model to display where the problems are going on, and that'll support identifying trends within the work orders. So in order for us to get to the machine learning, we started with a collection of data of just under 150,000 work orders that were previously labeled by FM staff with the problem type. Now, because we used a supervised machine learning method, we had to ensure that this data was labeled accurately in order to not confuse the machine learning program. So we verified about 45,000 of these requests, and we found that only less than 1% were labeled inaccurately. So that deemed this data set appropriate for the machine learning algorithm. Next, the data mining was conducted through the MapReduce method. So we essentially we sorted the data by time, location, and type of problem, and then we added all that together to determine the frequency of each type for each parameter. Now moving on to the machine learning, we use three different machine learning methods here. We use term frequency, inverse document frequency, term frequency, inverse category frequency, as well as a random forest model. So our term frequency models evaluated the frequency in which words were used in work order descriptions and weight those in inverse proportion to the frequency in which those words were occurring in either the document or the category. So that led us to find words that were commonly occurring in certain problem types. So, for example, plumbing might mention pipe, but something like the, or please, or thank you that appears consistently across every work order was ignored. Finally, the random forest model grew a tree of words which produced sentences, so that the trunk of the tree was essentially the first word, and every branch coming off that tree afterwards was every possible word that was used after that word, and it identified the most common combinations of words within each problem type category to label a problem type. And finally, we linked that to the BIM model. So it was, just like I said, with the data mining, those results of the data mining were linked to the BIM model in order to visualize this. And this just added for a more user-friendly approach to the data mining process. Okay, so moving on to the results of the data mining. Here we have frequency problem type by location, or no, sorry, by time. And this looks like a lot of information right now, but if you look a little closer, we can see that with HVAC, pretty much it's experiencing a consistent spike at the end of every year, and that aligns with our seasonal changeover from heating to cooling at Ryerson. It takes about 1 week, and that results in a lot of HVAC complaints coming from the users of the facility. Now, that's not necessarily new information because we know that it takes about 1 week for it to change over, so we do expect a spike in work order requests for HVAC. But if we dig a little deeper, we can find that those spikes in HVAC also align with the spikes in plumbing. So this is what I would consider new information because now we're finding that those plumbing problems are likely associated with the increase in HVAC problems. So before it might have been a thermal discomfort issue with HVAC, which we might consider inevitable because of the changeover. However, because it's aligning with plumbing, now we can find that maybe we're experiencing pipes bursting or leaking, which is a fundamental issue. Similarly here, we have frequency of problem type by location and time. And again, it's a lot of information to look at, but if we dig a little deeper, we can see that the buildings, Jorgensen, Library, and the Podium all experience the same trend in the frequency of work orders submitted. And that's because these three buildings are attached and share the same systems. And similarly, that occurs for all the Kerr Hall, North, East, South, and West buildings. So in the data, we can see that because these are, like they all align, it's not necessarily new information, but this shows that it's possible to mine the data to determine root cause analysis. So for the results of the machine learning here, we found that in terms of accuracy, the random forest model produced the highest and most consistent accuracy. And that's also reflected in the confusion matrix here. So we can see across the diagonal, the random forest has a nice white diagonal and red everywhere else, whereas the term frequencies got somewhat confused and they were sometimes labeling it correctly, but sometimes incorrectly, or they were finding multiple possibilities that included the correct answer, but also included other possibilities that weren't necessarily correct. So we can conclude here that the random forest model is the ideal model for this situation. And now for the BIM visualization. So here we have a heat map, or I should say a magnitude map of two cold issues occurring along a floor plan. So we can see here that all of our maintenance requests are clustered along the center of this floor plan and not really on the outside. So we can assume that we have an HVAC issue occurring in that localized area. Now this model can also be played around with. This is the dashboard for the BIM model that allows you to change what parameters you're looking at, whether it's by floor or by room, or what type of problem you're looking at, whether it's too cold, too hot, plumbing, etc. So for this, we can conclude that machine learning can accurately predict the problem type with great accuracy, greater than 90% with the random forest model, and also that the BIM visualization provides improved information to facilities management staff in terms of spatial, temporal trends, and systems relationships. To improve this, we found that within the problem descriptions and the problem types, there's a lot of general and miscellaneous being assigned to problems. And that was because there wasn't enough information submitted by the work order submitter to determine exactly what the problem was. So in order to improve the accuracy of the model, we need to get rid of the general and miscellaneous types. But in order to do that, we need to improve the data that we're receiving. And I'll get to that in a second. That's the future work we're going to do. But before we get there, I just want to acknowledge that the limitations of the study include that we only studied a single campus. So at our campus, we have our own way of delivering work orders to the staff, and through our method of user-submitted work orders, that allowed for the prediction of problem types. However, in a different submission process, you might not receive the same amount of accuracy. Also, there needs to be communication between the facilities management data and the BIM model in order to support scaling of the model. And also, in order to have this as a real-world deployment, we need greater accuracy than 90%, because I think anything less than maybe 98%, you're going to do more harm than good in terms of predicting the problem type, and if it's wrong 2% of the time, that might cause a lot more problems later on. So we just finished up the classification prediction, and we were able to classify what I would call a level 1 problem, or a level 1 problem type. So that lets you know whether it's HVAC, plumbing, electrical, etc., but it does not tell you what type of problem within that trade is the problem is. So within HVAC, we don't know if it's a fan issue, we don't know if it's a thermal issue, all we know that it's an HVAC issue. So in order to improve that, we're developing a set of clarifying questions which we'll deploy in a case study, which will provide more useful information to the facilities management team. So here's an example of the work orders we're receiving from the submitters, and the one in blue is a very good example of a work order submission because they specify that the receptacle has no power present. So we know that it's an electrical issue, and we also know that it's a problem with a power outlet. The one in red, I would say, is a not so good issue, or a not so good submission, because all we see that is lights could not be turned on down here on the second floor of Jor. So we know that the lights aren't going on, but we don't really know if it's necessarily a lighting issue, or if that's a whole power out issue in that room, or if it's just a light bulb issue. So some questions that we might want to ask for this is, do other outlets in the room have power? Do other fixtures have power? Or did you hear like a pop when the light went off that would say that maybe it's the ballast or the light bulb? So those questions will further allow us to achieve greater information to the FM team, which will support the root cause analysis. So as I said just a second ago, this recommender system will be deployed at the end of this summer or at the beginning of fall of this year, and we will evaluate the results of that in 2018. And as I said at the beginning, the whole idea behind this is to support root cause analysis of facilities management problems, which will hopefully allow us to optimize facilities management activities. And before we finish up here, I'd just like to acknowledge the Brain Alliance for funding this project, our faculty and department, as well as Ryerson International for providing funding for travel here, as well as the Facilities Management Department at Ryerson for letting us use the data and participate with them. So thank you, and I'd like to take any questions you might have.